Okay, everyone, we're going to go ahead and get started for the Sustainable Phosphorus webinar series. I'm Matt Schultz with the Sustainable Phosphorus Alliance, and our topic today is critical challenges managing phosphorus production wastes. Who we are, we're the Sustainable Phosphorus Alliance. If you haven't heard of us before, we serve as North America's central forum and advocate for the sustainable use, recovery, and recycling of phosphorus in the food system. And we're supported by a great slate of member organizations who help finance this webinar and our other activities as well. If you're interested in becoming a member of the Alliance as an organization, please reach out to us and we can have that discussion. We don't have memberships for individual people, but there are ways you can follow us, including through our YouTube channel, which I'll be talking about here in a second. We also have a newsletter and some other and social media, and all that stuff is accessible from our website, which is at phosphorusalliance.org. Okay, we get on to the topic of today's webinar. Just sort of tee this up, you might have heard that phosphate rock is now listed as a critical mineral in the US. And that's in part because of the vital role that it plays in everything from food production to pharmaceutical production to the manufacture of electric car batteries. And turning that rock into raw materials needed to make all these products requires processing, and processing almost always generates some sort of waste. In this case, in the case of phosphorus, some of these wastes can be toxic and radioactive, so we need to figure out how to manage them more sustainably. And so today we're going to be looking at case studies of environmental pollution from phosphate rock processing, various pathways to remediating waste sites, and perhaps pathways to perhaps using the waste materials more safely. And so we have four great presenters, as we always do at this webinar series, and I'll be introducing them in the order of their presentations at the top of their presentations. So the first presentation today is coming from Dr. Elise Morrison, and she's an assistant professor in the Department of Environmental Engineering Sciences at the University of Florida. Her research program focuses on nutrient and organic matter cycling in wetland and estuarine systems, with an emphasis on microbial ecology and chemical biomarkers. Many of her ongoing projects evaluate the biogeochemical effects of anthropogenic disturbance, including investigating the ecosystem effects of the 2021 Piney Point phosphogypsum release in Tampa Bay, Florida, which we'll be talking about today. So Elise, if you want to go ahead and share your screen, we can start your presentation.
Okay, thank you, Matt, for the introduction, and thank you all for the opportunity to speak with you today. And so today I'll be focusing on phosphogypsum, and I'll be talking about its environmental effects and discussing some potential alternate uses for phosphogypsum as well. And as Matt mentioned, I'm an assistant professor in the Department of Environmental Engineering Sciences, and I've included my contact information here in case you would like to reach out. So phosphogypsum, as you may be aware, is waste generated from the wet acid production of phosphate fertilizer and phosphoric acid. And so this is predominantly made of calcium sulfate, but has impurities such as fluoride, lead, calcium, phosphorus, heavy metals, and also naturally occurring radionuclides. So these radionuclides occur naturally in the phosphate rock that's mined and can be concentrated over the course of producing phosphate fertilizer. And so for each ton of phosphoric acid fertilizer that's generated, it's estimated that there's 4 to 5 tons of phosphogypsum produced. And so this results in a very large amount of waste that needs to be addressed. And globally, it's estimated that 4 to 5.1 billion tons of phosphogypsum has accumulated. And you can see these key areas of major phosphogypsum deposits in the map below. And so we have a few different options when we produce phosphogypsum waste. Most of it goes into phosphogypsum stockpiles, and only 15% of this phosphogypsum is reused. So the rest is either in stacks or on occasion discharged to water bodies as well. So these are large above ground stockpiles of the waste, and they're often found close to coastal areas and regions where phosphate fertilizer is produced. And due to their proximity to coastal areas, they can pose unique environmental risks. And so they're often susceptible to leaking into the subsurface or superficial water bodies. And the majority of them are found in Florida, China, and Northern Africa, although there are other phosphogypsum stacks around the world. And so one of the main environmental concerns that we have associated with phosphogypsum stockpiles is these potential pollutants that can come from the stacks. So we have phosphate ore that is naturally high in radionuclides, depending on where the material is sourced. We also have commercial sulfuric acid, and we can have heavy metals contributed from that. And this results in fertilizers going to market, but then the disposal of this material results in these phosphogypsum stockpiles. And there are a few different routes that we can have environmental pollutants generated from these stockpiles. So we can have atmospheric pollutants that can result in human exposure in adjacent regions. We can have leachate that migrates into water bodies, and that can result in biomagnification in the concentration of pollutants and subsequently to consumers. And we can also have heavy metals and suspended solids transported into sediments, and these sediments can then impact agricultural and residential areas. So due to the numerous environmental concerns that we can have from phosphogypsum stockpiles, we want to make sure that we are minimizing the production of phosphogypsum and potentially reusing it, which we'll go into later in my talk and also later in this seminar. But before we do that, I wanted to give a case study of the Piney Point facility in Tampa Bay, Florida. And so this facility was established in 1966 and decommissioned in 2001. And over the course of its history, starting in the 1990s, there have been episodic spills that have occurred into the adjacent bay, and specifically into certain back bay regions, such as Bishop Harbor. And so you can see that these episodic releases have large volumes of waste and a processed water mixed with dredge water that have been released into the bay. And so the event that I'll be focusing on today is the 2021 emergency discharge of 215 million gallons of this water released into the bay. And so in March 2021, it was discovered that there was a tear in the liner of a holding pond at this facility. And this prompted the Department of Environmental Protection to release an emergency order to allow for discharges into Tampa Bay to minimize the risk of adjacent communities. And so this resulted in 215 million gallons of wastewater into Tampa Bay over the course of March 30th to April 9th. And this discharge had nitrogen and phosphorus concentrations that were much higher than normal for the bay. So the discharge was 210 milligrams per liter of ammonium and 140 milligrams per liter of orthophosphate. And normal bay conditions were 0.019 and 0.049 milligrams per liter. So much higher than usual for normal bay conditions. And the high nitrogen is from the production of diammonium phosphate from the facility. And so this high pulse of nutrients prompted concerns about algal blooms and ecosystem effects. And there were also groups, and namely at the University of South Florida, focused on looking at contaminants as well. And so this is just a brief timeline of what happened directly after the event, but my team, in collaboration with the Tampa Bay Estuary Program and the Sarasota Bay Estuary Programs and many other monitoring groups, were out observing conditions over the course of the summer, and then we continued monitoring 2 years out as well. And so on March 30th, we had discharges that began. Discharges ceased on April 9th, so a very brief window of time. And we saw soon after that there were localized diatom blooms that occurred. And so diatoms are a really quick responding phytoplankton. They grow fast when abundant nutrients are available. And so that likely influenced their growth. We also noted that Karenia brevis, or red tide, occurred in the bay during that summer. And there were other unusual conditions in the bay that could have also contributed to Karenia brevis. So, for example, there was a low rainfall, which resulted in high salinities in the bay, and that may have also influenced red tide. And just to note, red tide originates in the Gulf of Mexico and then is transported to the near shore and into the bay. So it did not immediately cause red tide, but may have exacerbated it. And then eventually conditions became relatively stable around August or September of 2021. However, we're still investigating some of the potential long-term effects in both sediments and seagrasses. And so one aspect of this work was looking to see if we have a historical record of past discharges from the event. And so my student Amanda Chappell took cores in Bishop Harbor, which was the site of prior releases, and Piney Point Creek, which was the site of the 2021 release. And we developed chronologies based on lead 210 dating and found that where these blue bars are, those are regions of past known releases, and we see increased phosphorus accumulation rates associated with those events. And so this indicates that these past events have caused nutrient accumulation in these coastal sediments, and just further highlights the need for responsibly managing our phosphogypsum and ideally reusing it. So we've talked a lot about the environmental impacts, but there are ways that we could potentially revalorize phosphogypsum to have it be used for alternate productive uses. And so you can see in this first table, we have the countries that generally use phosphogypsum, both produce and use phosphogypsum. And so you can see that China uses the majority of their phosphogypsum. And it's important to note that due to the source of phosphogypsum, it can have varying levels of these contaminants that are of environmental concern and varying levels of radioactivity, which can limit its use in other materials. And so overall, it's been used in construction and cement production. So it's a setting regular for cement. It's used in gypsum plaster. There's been studies looking at using it as roadbed material. We'll hear a little bit more about it as a soil stabilization amendment and its use as potential fertilizer. But overall, building materials have been banned in 1990 in the US and discontinued in 1992 in the EU. However, these are still, depending on the source of the phosphogypsum, they're still potentially viable options. But with my background in microbial ecology, what I think is a very interesting avenue is can we recover some valuable materials from phosphogypsum by harnessing the metabolisms of microorganisms. So I think this paper here really nicely summarizes it. Due to the limited ways to safely dispose of, store, or reuse phosphogypsum, biological treatments to recover value from phosphogypsum is a promising option. So microorganisms are very diverse and they have many different metabolisms. And so we can actually use their metabolisms to extract valuable materials that would otherwise be inaccessible from waste streams. And this is usually referred to as either biomining or bioleaching. And so phosphogypsum contains valuable materials, including elemental sulfur, rare earth elements, and other critical minerals, which have shown, some of which I have shown here. And so while these concentrations may not be high relative to primary minerals that are normally mined, the large volumes of phosphogypsum waste and the desire to decrease its environmental risk make it a appealing potential source of these materials. And here you can have an estimate of phosphogypsum's rare earth element concentrations relative to some other alternate waste streams. And so the way that this is done, it is either through the use of bioleaching or bioseparations. And these approaches, specifically bioleaching, are widely used for other feedstocks and waste streams. So industries focused on recovering copper or gold from mine tailings have used bioleaching to access materials that otherwise were inaccessible. And so we can use either existing microorganisms, or there have been studies that have engineered microorganisms to optimize their ability to bioleach rare earth elements, for example. And the benefits of this is that it often requires less energy and can be more environmentally friendly, because in certain circumstances, for example, you can have microorganisms that produce sulfuric acid rather than relying on commercially produced sulfuric acid, and thereby also decreasing your operational costs as well. And so there's a few different ways that we can do this. We can either do it directly and take the microbe and the critical mineral feedstock, add some additional elements that help promote the microbe's growth. And this can be done either in a heat method or a stirred tank reactor scale. In other cases, we can actually add other microbes as well as a carbon source, let them grow initially without the critical mineral feedstock. This produces a biolixiviant, which is like a mixture of acids that can be used to then release these and solubilize these metals from this feedstock. And so with these two approaches, this has been really promising for many different waste streams, and phosphogypsum is potentially one of these as well. And so here we can see in this chart that phosphogypsum can be used with sulfuric acid producing microbes at both a flask scale and a reactor scale to produce a usable rare earth product. So these studies have used biological treatments to recover rare earth elements and elemental sulfur from phosphogypsum. And these often focus on microbial production of organic acids or sulfuric acid. And in one study, they found that two-step bioleaching, so similar to that indirect approach that I described earlier, resulted in greater extraction. And in some cases, we can extract up to 55% of the rare earth elements from phosphogypsum waste. So these approaches, if they could be scaled up, could greatly improve the circularity of the phosphorus economy and help address the key challenge of phosphogypsum waste. And so in this overview, we have phosphogypsum that's generated, and it can either be stored long term, but there are associated environmental and actually also operational costs around that. And instead, we can look towards UN's Sustainable Development Goals to try and decrease natural resource use and increase waste valorization. And by doing this, we can take these stockpiles and start exploring their uses in a variety of different applications, including rare earth element recovery. So with that, I'd like to thank you for your attention, and I would be happy to answer any questions during the Q&A.
Great, Elise. Thanks so much for that presentation. We did have one question, which actually was the same question I was going to ask, and it comes from Adam Herges, which is, what is the cost of implementing bioleaching in stacks, and has this ever been done at scale? Is this, when you mention these reactors, are those actually commercial companies, or are they sort of things, pilot facilities at universities? Where are they sitting right now?
So predominantly they're pilot facilities at universities. I don't believe there have been any published studies, at least, applying it on the stack level. There has been interest in using these bioleaching techniques for, say, spent light bulb waste streams in national labs. So in Idaho, they've been working on this for quite a while. So they've scaled it up through the national labs. But yes, to my knowledge, actually applying it on a phosphogypsum stack has not yet happened.
Okay, great. And then we have another, it looks like, I'm not sure if this is a question or a note. Yes, it's a question. So this comes from Ronald from Proman in Austria. He said, regarding some of the data shared, I was wondering wondering on your thoughts of why the stocks of phosphogypsum are not directly on the main spots where phosphate rock is globally extracted, neither the main phosphate rock processing spots. I guess that's, yeah, so it's looking at, I guess he's asking about the geography, or the physical location of PG stacks versus where they're mined. And
Yeah, so I believe it relates to the proximity to both additional sources. So for example, you'll need to add sulfuric acid in order to produce phosphate fertilizer. So having a facility that's slightly removed from your mine is that's beneficial. And then also for transport of that fertilizer afterwards as well. So I believe that's why they don't co-occur directly immediately where the mines are.
Right. We're probably not going to get to all these questions, folks, because we have other speakers we have to get on deck. But we've got time for probably one more here. So there's one from Ed Weinberg, which is for the gold bioleaching example. Gold is over $4,000 per ounce now. Do you have any sense of if it's a profitable operation or?
So I haven't looked at the costs breakdown for gold specifically. I believe that it has been very useful in certain waste streams that, for example, if you're trying to remediate mine tailings and trying to get some additional value out of the remediation already. So I believe that it's beneficial to extract some additional value.
Okay, great. Thanks, Elise. And Elise, if you wouldn't mind, there's some other questions in the Q&A, and if you have a chance to sort of address those while Jake is giving his presentation. I appreciate that.
Of course.
Great. Thank you so much again, Elise. And so we're going to go to our next speaker, Jacob Sloan. So Jake is a process engineer and senior project manager for Case Warbonnet with more than 13 years of experience in environmental remediation, operations and management, consulting, and client representation for complex environmental and Superfund sites. He specializes in the management and remediation of elemental phosphorus, phosphine, and associated production byproducts. Jake has prior experience working on investigating and remediating projects in the Mid-Atlantic states. So, Jake, if you want to go ahead and take over, please do.
Well, thank you everybody for the time and attention this morning. My name is Jacob Sloan. I'm with Case Warbonnet. We're an operations and maintenance and remediation contractor, and we perform work at a historical elemental phosphorus production facility. And so I'm here to speak with you all on elemental phosphorus production and how its associated waste streams can introduce different forms of phosphorus to the environment. In my presentation, we'll review handling and remediation techniques for the different forms of phosphorus discussed, and then we'll look into beneficial reuse options for remediated sites and waste materials at the facility. So, brief agenda. We'll do an introduction to elemental phosphorus, different than phosphoric acid production process. We'll talk about characteristics and industrial uses. Then we'll look at the P4 facility in question, look at waste streams and potential remediation techniques, and then we'll look at reuse cases to conclude. So introducing elemental phosphorus, it's a very unique material with unique characteristics. First, it does not occur naturally. It is a man-made material from phosphate shale. It spontaneously combusts when it is exposed to air. So if you had a piece in your hands while watching this webinar, it would likely be burning at the moment. It ignites at a low temperature around 86 degrees Fahrenheit and burns very hot at 2000 degrees Fahrenheit. Its reactivity increases as temperature increases. So as it starts to ignite itself, it increases its temperature, causing it to burn faster and faster. It generates phosphorus pentoxide, a white particulate smoke, or P2O5. And it is also insoluble in water, making water a very handy material to manage the phosphorus. Pictures on the right, up above, I'm circling it with my cursor here, is an example of production grade phosphorus. It's a white, waxy looking material. This was just drawn out of a water cover. If it were left out of this water cover for much longer, it may turn into the photo below, where there's elemental phosphorus pieces igniting in air with flames behind it and the dense white particulate smoke. Phosphorus, elemental phosphorus, has many industrial uses. I think many are familiar on this webinar with its uses in fertilizers and crop protection products. It's also used in the food industry, in food grade preservatives, many consumer products. It has metallurgical uses for steel industry and coatings. It can be converted to phosphine gas. We'll speak on phosphine in a little while and the usages for that. And it has been used to make matches and fireworks. So moving to a review of phosphorus production, the waste streams, and how different forms of phosphorus may be introduced to the environment from such streams. This slide is a depiction of a site that Case Warbonnet works with and the prevalent impacts from the historic production. The site's no longer in operation, but when it operated, we used an electric arc furnace to produce elemental phosphorus, and that production method generated waste streams of P4 laden waste. The waste would be stored typically in waste storage areas, which were usually consisting of holding ponds. And those ponds may be lined or unlined depending on the best management practice and the regulations at that time. This facility in question and many P4 facilities began in the early 1900s, and some even operate today. So regulations change. The next slides will review these phosphorus forms. We have the phosphorus impacted solid waste. We have phosphine gas generation. And then we have highly soluble orthophosphates potentially impacting the groundwater table. And we'll discuss how they're remediated. It is important to note that remediation, the industry that I primarily work in, is managed under federal or state managed programs such as EPA, CERCLA, and RCRA. So these techniques are typically well vetted with the EPA. So looking at the elemental phosphorus waste remediation, P4 impacted solid waste, as I mentioned, is typically present in the waste storage areas at high quantities. There can be residual impacts from spills or industrial handling over the history of the facility as well. The purpose of the remediation of this material is to prevent physical contact to human and environmental entities. So when considering remediation techniques, it's important to evaluate the risks of managing and handling the P4. As I mentioned, it ignites in oxygen, so reducing any exposure to oxygen is key. The most common method of remediation is to leave it in place and install a cap or cover system. This is also typical of many other CERCLA and RCRA managed sites, especially sound when combined with institutional controls and monitoring methods. So our CSM example picture here, we have this thicker brown layer laid over the industrial site facility, keeping the phosphorus impacted waste in place and protecting any human or environmental entities from risking any contact in the material. There are other remediation techniques for phosphorus wastes. They include stabilization and solidification in situ, which is mixing the materials with maybe a cement or bentonite to stabilize and harden the material and prevent any mobilization. There's also ex situ methods, which is removing the materials from the ground and performing treatment. However, as I note here, all of those methods require the material to be excavated or at least exposed, and it really introduces that risk of having the P4 waste come in contact with oxygen and increasing its potential to ignite. If P4 impacted material or waste is needed to be handled, there's many safety measures that need to be in place to do so. I'll go through a short list of them. First, if you are aware that you may come in contact with elemental phosphorus impacted materials, it's very critical to study that site's usage so that you can understand where the material may exist, what the likelihood of encountering it is, maybe concentrations of the waste, and additionally, just how to avoid it if possible. Having a strong safety culture with the personnel performing the work, consultants, contractors, etc. Doing that with strong procedures, strong trainings, and great practice are key. Having the proper tools, equipment, and personal protective equipment, or PPE, to handle the materials. And I have example photos here. So in this upper photo, we have tools and equipment needed to address safety oversight of a drilling operation with small quantities, yet you see pickup truck, skid steer, lots of hand equipment. On the bottom, a larger operation where containerization of the waste is necessary, and as you can see, even more tools and equipment are necessary to safely handle the material and perform the work. Lots of heavy equipment, designed work areas, and etc. Fourth, when handling elemental phosphorus, it is critical to minimize its exposure to oxygen and prevent ignition. And to do so, using clean sand or soil and water is very helpful, as it smothers the material and prevents any contact with oxygen. An example in this photo down here, we're opening a drilling core, and you can see the material just starting to ignite, some white smoke coming off of it, and we are about to pour all this sand on it to remove the oxygen source from the material and prevent ignition. Next, we'll look into our second phosphorus form potentially introduced to the environment, and in phosphine gas generation. Phosphine is a toxic, flammable, colorless gas. pH 3 is its chemical equation. It's a potential waste product associated with phosphorus production, and at the site we work with, it's primarily generated from the hydrolysis reaction of elemental phosphorus and water in alkaline conditions. All three ingredients need to be present in order to produce phosphine in measurable quantities. You may think back to the slide previous where I mentioned managing phosphorus with water to prevent ignition. That is possible to do, and it's unlikely to produce any measurable quantities of phosphine gas. That third ingredient of a basic pH, those hydroxyl ions, is necessary. Phosphine has many industrial uses. It's used in the semiconductor industry, used in the fumigant industry for large grain storage and transporting applications, rodent side, and then also in the synthesis of flame-resistant materials as well. So when we get looking into phosphine remediation and treatment, what our goal is to prevent exposure of the gas to any human or environmental entities. So therefore, we want to attempt to contain it and potentially, if the levels are high enough, collect it for treatment. A great remediation method to collect it and treat it is through the use of a soil vapor extraction system. And we have something of an example shown in our site CSM image here. Soil vapor extraction consists of piping within the area where the phosphine may be generated. That piping collects the soil vapors, which contain the phosphine gas, and convey it to a treatment system. The treatment system treats or removes the phosphine from the airstream, typically using granular activated carbon. Carbon's a really great material to clean phosphine from airstreams. There are thermal oxidation methods as well. However, in a remediation setting, those tend to be much more expensive than granular activated carbon. However, thermal oxidation in industrial settings may be a different story. And then, as you see below, again, our goal is to contain the gas generation into a known area so that we can install the proper extraction equipment. So capping and cover systems can be very helpful in doing that. So again, you see this brown cover system over top. When working with phosphine gas or managing materials that have the potential to generate it, again, robust safety systems must be in place. It's a gas, so monitoring the air in which you're breathing is critical. And to do so, you would use phosphine monitors. An example of one is shown here. They are typically comprised of electrochemical sensors and are very handheld and ready for use in industrial hygiene monitoring situations. Again, where you're monitoring the breathing air to measure the risks of exposure to yourself with the phosphine gas. At any given site, if phosphine generation is a potentially, we could employ environmental monitoring procedures such as surface level scans, soil flux measuring, which is measuring the amount of gas emitting from a surface area, and you can take the reading and input it into a risk calculation to determine the risk of exposure. And then finally, continuous perimeter air monitoring to monitor if there's a potential for the gas to migrate off-site. And then finally, as I mentioned, it's a toxic gas, so safety protocols and procedures for working with phosphine must be in place and well cultured with the work crew. So finally, our third phosphorus form will look at orthophosphate impacts to groundwater due to the phosphorus contaminated wastes. Orthophosphate has a very high solubility, so it tends to be the predominant phosphorus form in groundwater at our site in particular, and likely many others. Additionally, at our site in question, there are non-reactive phosphorus impacts that are present, and those are in the form of hypophosphite at our site, and this was again due to the P4 production process. Looking at remediation techniques, our goal with remediating the groundwater is to prevent any consumption of the groundwater or expression of that water in surface water bodies, causing risk to human and environmental entities. Primary remediation methods to prevent that risk tend to be pump and treat systems, which are installations of extraction wells, which will pull the groundwater from the earth and route it to a groundwater treatment facility. The treatment train for orthophosphates is commonly coagulation and flocculation. And at our site in particular, there is a potential polishing step that may be required to fully remove the orthophosphates from the groundwater stream. As I mentioned, the non-reactive phosphorus needs treatment via a side stream process by oxidizing the hypophosphite to orthophosphate. For those of you that are interested in that non-reactive treatment process, there is a case study to be presented at the Patel Chlorinated Conference in May 2026. So anybody is welcome to sign up and attend that. Additionally, third time is a charm. Cap and cover systems are also very helpful with groundwater remediation. They're typically installed to support the remedy because they prevent stormwater and surface water from infiltrating into the waste materials, which can then mobilize the contaminants downward to the groundwater table. So at our industrial facility in question, there are potential reuse cases that are either being implemented or being investigated. Elemental phosphorus production facilities have great access to infrastructure. As I mentioned, the electric arc furnace is the main production method. That process requires lots of power access. So these historic sites and brownfields are likely to have good access to power facilities. Additionally, great transportation needs via highway and rail. So it suits that a potential site reuse option can be another industrial facility that requires that type of infrastructure. Additionally, the capping or cover system process usually leaves a well-graded level site, and renewable power is a great option where you have these large acreages that solar panels can be installed or windmills. We are looking into waste material opportunities of reuse. When you have elemental phosphorus-laden wastes, are there ways that the phosphorus can be harvested from the material and beneficially reused, potentially turned to phosphoric acid for all the uses of that? However, a reminder back to our remediation cases that this would require excavation and exposure of the material, potentially introducing oxygen and introducing that large safety hurdle of oxidizing and igniting materials. So something to evaluate and overcome on that option. Phosphine gas is generated. Can that be collected and beneficially reused? And then also orthophosphates in the groundwater treatment streams. Can the orthophosphates be removed from the treatment streams and beneficially reused perhaps in fertilizer type scenarios? Additionally, similar to fertilizer production facilities using wet acid processes, elemental phosphorus production also relied on phosphate mines. So these facilities tend to have historic mines, and there can be beneficial reuse cases there through waste shale rock piles, the other minerals that may be available depending on the geology. So finally, bringing our initial site conceptual model to a conclusion with all of our remedies installed, we have our cap and cover systems providing 3 different types of protection of the impacted materials below. We have our SBE system collecting potential phosphine gas generation and treating it, and then the groundwater treatment facility remediating any groundwater impacts, leaving a site that is well open with great infrastructure for potential industrial reuses and renewable power. that concludes it for me. Again, thank you everybody for your time and attention, and contact info is here.
Great, thank you, Jake, for that presentation. We did have a question that came in through the chat, but I want to make sure we have time for our last two speakers here. So if you wouldn't mind answering, it looks like two questions here in the Q&A offline, that'd be great. And we'll go ahead and move to our next presentation. But thanks again.
Will do. Thank you.
Okay, I'd like to go ahead then and introduce our next speaker, and I'll be advancing his slides. So Dr. Paolo Pavanato is currently Associate Professor at the University of Sao Paulo and the College of Agriculture. He has expertise in soil fertility and fertilizer use in agriculture, working mainly in phosphate fertilizer management for improving use efficiency and crop rotation. Moreover, he's focused his research on soil P dynamics and production systems influenced by cover crops and soil management, as well as the use of cycling of environmental residues as sources of nutrients for plants. More recently, he's joined the Sea Carbon Project for better management of fertilizers to improve carbon accumulation in agricultural soils. So, Pavanato, I'll go ahead and advance your slides. Are you ready?
Yes, please.
Great.
Okay, go ahead. Thanks, Matt, for the introduction, and thanks for the opportunity to speak a bit here about the use of phosphogypsum. Here we are focused on a case study in Brazil, where we are trying to be more friendly using this residue of phosphate industry in the agriculture as agricultural amendment. So please, next slide. As mentioned by my colleague, Dr. Elise, from the first presentation, Brazil is nowadays using more than 100% of our production in agriculture. So that's interesting fate for this phosphogypsum, because we know that we have a big improvement in soil profile when we are using this phosphogypsum, and crops are responding very well. So when you please move for the slides, just go ahead, keep going. So the production system is this in Brazil is in this red points here. We have two main regions, main place to produce phosphogypsum, and also we have a natural phosphogypsum production in northeast Brazil. And the main production area, for example, for soybean production, that is the main crop for Brazilian agriculture, is in the center-west part. In Mato Grosso is the biggest one, and Goiás, and so on. So the distribution of this phosphogypsum is according to the transport of the crops, the crop grains. Then the trucks return to the farms with this phosphogypsum. So it's a interesting logistics for using this phosphogypsum in agriculture. Please go ahead. And when you are considering the total production of phosphogypsum in Brazil, we are producing around 7 million tons nowadays. Mosaic is the predominant industry in Brazil for phosphorus, and then for phosphogypsum. And we are using agriculture a bit more than that. We are using around up to 9 or 10 million tons of phosphogypsum every year. As I said, we have a natural production, a natural gibbsite in northeast Brazil. In that area, we produce around between 3 and 4 million tons of phosphogypsum of gypsum that in that occasion, and most of them is used for cement production. So around 1 million ton is used for agriculture in northeast Brazil. The other is just phosphogypsum produced from the phosphate industry. And the main crops, maize, soybean, and sugarcane and coffee are the main ones that we use for using this phosphogypsum. One important point considering our agriculture in Brazil is that the price usually limit the use of phosphogypsum, because the farmers don't want to pay more than $50 per ton in loco, in your property. So if the price is too high, farmers don't use. So that is one important point for distribution and improvement of use of PG in Brazil. Please go ahead. So when you're considering the Cerrado region, the main central part of Brazil, we got a huge development of agriculture in the last 2 decades in this region. But Cerrado soils or savanna soils are usually acidic and have low calcium content, high aluminum content in the profile, and when we are using just liming, for example, for improving the pH, this lime doesn't move in the profile. So when we are using phosphogypsum may promote an interesting movement of calcium sulfate and magnesium sulfate in the profile, and also complexing aluminum with the sulfate. So we have a huge effect in the soil profile when you're using phosphogypsum, because sulfate, you're going to complex aluminum, so aluminum will be not toxic anymore, and also you move calcium in the profile. So when we have calcium in the profile, roots will develop well, and plants will explore better the soil profile. This is really important in drought seasons or in lack of rain in specific points of the crop development, especially, for example, at flowering stage. So this is really important that we have a root developed in deep layers to explore water in these restrictive conditions. So that's really important for using PG in Brazilian agriculture. Please, next. So I'm going to show some results here, considering this important effect of phosphogypsum in the profile. One of these is some studies were done by Embrapa. Embrapa was established in Brazil as the main research agency nowadays for the general crops of Brazil, and it was established in 1970s. And they did a wonderful job in exploring the Cerrado region of Brazil. So this is a study that they did for understanding the effect of phosphogypsum after application of some years of application in the soil profile. So for example, here it was used at 5 tons of PG, and they evaluated in one specific year that we have a drought period of 25 days. So at flowering stage of maize. So we can see the development of the rooting system, and also we can see the water availability. So when the root system is deeper, plants can explore this water in profile. Please, next. So the response of this supply of water or better development of the rooting system is the exploration of water in periods of lack of water. So here we're just considering the root distribution, the percentage of root distribution when we apply or we don't apply phosphogypsum. So we can see that in the top 30 centimeters, almost 90% of the rooting system is there when we don't apply phosphogypsum. When we apply phosphogypsum, only around 50% of the rooting system in the top 30 centimeters. We have much more roots in the deeper layers, what may promote a better resistance to drought stress. Please, next. So this management have a huge consequence on crop development because of the distribution of nutrients in soil profile. So here you can see results of sulfate and also calcium magnesium. So this was evaluated after around 4 years after phosphogypsum application. So we can see that we have in the left, we have a lot of sulfate available in deeper layers, like from 10 to 80 centimeters. And also we have more calcium and magnesium in deeper layers because sulfate promote this better distribution in the soil profile. This obviously will have consequences, as we can see in the results here. So this is a mean yield that was got for maize, for wheat, and soybean when using or not using phosphogypsum. So we can see here, these results are from 1980s, 1990s. So we can see here improvement in more than 2 tons of maize per hectare using phosphogypsum. Wheat to improve at 1.3 tons in mean, and also soybean improve a little bit after using phosphogypsum. So this is really important for stressing conditions that when we have a lack of water. Please, next. And another result, this is a more recent result from the colleagues here, Bossolani and collaborators. They evaluated the effect of the chemical effect when using phosphogypsum and also lime. So we are evaluating here phosphogypsum, lime, and lime plus phosphogypsum. So we can see here in the blue and green lines that when we have lime and we have phosphogypsum, there is a huge improvement in pH, especially in the top layers. There is a huge improvement in calcium availability and also in magnesium availability. But one important point here is that, for example, phosphogypsum doesn't change the soil pH. So phosphogypsum doesn't affect the pH. Phosphogypsum will affect calcium availability and especially the movement of nutrients in the soil profile. Please, next. When we see the results of this improvement, for example, here in shoot dry mass and also in grain yield, we can see that phosphogypsum doesn't improve too much. It was evaluated 2 seasons, no? The blue one is the first season and the brown one is the second season. We can see that just phosphogypsum doesn't improve too much the pH, the yield, the crop yield. But also, when we use phosphogypsum and lime together, we have a huge improvement because phosphogypsum is a complementary of the liming effect. So lime will promote the improvement of pH in the top surface, and phosphogypsum will work very well in soil profile to drop the aluminum content and improve calcium and magnesium in soil profile. So that's really important for yield stability over the time in the cropping system. Please, next. And here is, I want to show in this picture, it's not so easy to see, but this is a compile of data. This is a meta-analysis done by the colleagues from all the data generated using phosphogypsum in Brazil. And we can see here that they evaluated cereals and soybean. And also they evaluate up to 2 years and after 2 years. So please, next one, Matt. When we see here, when we have cereals and we have water deficiency, we have a huge capacity or huge improvement in the yield. So we can see yields improving from 10 to 15, 10 to 25%. So this is really interesting to see that dry seasons or dry periods promote a lack of yield. And when we apply phosphogypsum will turn over this deficiency or turn over this drought effect in crop yield. So that's really important. We can see that when we don't have dry season, when we don't have water deficiency, the effect is not so huge. Maybe 2%, 5%, 10%, no more. But when we have drought seasons, then we have a huge effect in crop response. Please, Matt, next one. And then some colleagues got data from soybean, wheat, maize, and consider all these 3 crops together. And we can see that the huge difference or the huge response in crop yield is usually observed when we apply up to around 3 tons per hectare. 3 to 5 tons per hectare of PG is the most responsive doses that we use in agriculture for improving crop yield. Obviously, we need to consider, for example, how long it was applied or when was applied and when we need to reapply again. And usually we reapply phosphogypsum when we need to reapply lime, for example. So, for example, in sandy soils, every 2 or 3 years, in clay soils, every 4 years, 5 years, we need to reapply to keep the positive effect of phosphogypsum in crop yield in agriculture in general. Please, next one. And another also important response is, for example, for perennial crops. And this is a really high value crop like coffee. Coffee, we have a huge area in Brazil, around 2 million hectares. And in coffee farms, they usually apply a lot of phosphogypsum in the beginning because phosphogypsum will force the plant to grow roots in deeper layers. So, for example, in the right picture here, we can see a huge root system up to 1.5 meters deep. So this is really important for coffee because usually in the coffee areas we have, for example, in Cerrado region, we have up to 5, 6 months of drought in the winter. So if we have a deep rooting system, we can resist much more of these drought periods by digging water in deeper layers. Please, next one. And this have a huge consequence because we may improve the soil profile. So here is a really recent result. This is a study made by some colleagues. It was not published yet, it was submitted, but it was evaluated after 15 years of application of phosphogypsum. It was applied here 7 and 56 tons of phosphogypsum per hectare. This is the treatment. And also it was evaluated in the raw and inter-raw. And we can see here, please, next, Matt. We can see here that when we evaluated the inter-raw, and this inter-raw usually is cultivated with cover crops like brachiaria and so on, we have a huge improvement in carbon stocks. So if you have a huge increment in carbon stocks, consequently we improve physical, chemical, and biological conditions of the soil. So this crop will produce more consequently about that. Please, next, Matt. And then we have a consequence in elemental availability, like calcium, we can see here in the raw, inter-raw. We have a huge increment in the green line here. You can see the big doses of phosphogypsum. This is, as I said, this was evaluated 15 years after coffee establishment. So it was a long time effect. So we have a huge increment in calcium availability profile. And next, Matt. And also we have a huge increment, for example, in phosphorus availability. So if we have availability, more available elements in the profile, we will have more root development, and consequently we have a better stability of crop production. So this is some results that we got from perennial crops. And also one question that everyone asks us is about radiological effects. So if you have problems with radons like a radio or uranium or thorium and so on. And this is one research done by colleagues from Paraná State, showing that after 14 years of application of phosphogypsum, and they applied up to 12 tons of phosphogypsum every 4 years, 5 years. So it was applied around 3 times this phosphogypsum in this area. They couldn't get any effect of radiological improvement in radioactivity or so on in areas that were used phosphogypsum in agriculture. So we don't have really a strong effect in these contaminants in our agriculture areas. Please, Matt. So just for final remarks here, phosphogypsum is one really important amendment for calcium and sulfur addition in our tropical soils. It improves a lot the soil profile, so this is really important for our crops. The combined application of lime and phosphogypsum increase rooting system and the ability of plants to acquire water and nutrients in deeper layers. So that's really important for crop stability. Chemical properties of soil profile also improve it, and especially under drought stress, the plants will export much better. And one last one is important for us is that there is no radiological effects detected using PG in Brazil in general. So more than 3 decades of evaluation, we didn't get any really strong effect in contaminating our soils with using PG. Just positive effects we could see in crop yield and also in root development of our crops. So that's my main message. Thanks a lot for the opportunity, and I'll be available for Q&A.
Hey,
Please.
thanks so much for that presentation. It's very interesting stuff. We do have a question in the Q&A here, Pavanato, but we've got about Well, we have about 25 minutes left, so I just want to make sure we get Mark's presentation in before we close out here. So if you wouldn't mind addressing that in the Q&A while Mark's doing his presentation, I'd appreciate it. I'm assuming you heard me and you're probably on mute. Okay, great. So we're going to go ahead to our final presentation, which is coming from Mark Vinovic from our member, NovaFos. And so Mark currently serves as the Chief Sustainability Officer at NovaFos Development and has been with the company since its inception. Previously, he was Vice President at, I hope I'm saying this right, Mark, Yamagi
Maggie.
Incorporated. Jamagi, okay. Managing the processing of titanium and zirconium waste for sale to aluminum producers. His earlier experience includes Director of Environmental Control for Weirton Steel Company or Corporation, which was an integrated steel mill producing 3 million tons of steel annually. And he began his career with the West Virginia Department of Natural Resources after earning his BS in Environmental Engineering from Penn State. So, Mark, go ahead and take it over.
Oops. So you guys see this?
Yes.
Okay. Yeah, I think I've kind of jumped ahead here, but let me go.
Yeah.
Okay, yeah, I'm going to talk about the processing of phosphogypsum for sulfur recovery and production of calcium silicates. Well, everyone has heard here today about phosphates are essential for food production, more recently becoming important for future energy products like LFP batteries. However, phosphoric acid production has sustainability challenges as it relates to the use and disposal of sulfur. Each ton of sulfur produced consumes almost, or of phosphate produced consumes almost 1 ton of sulfur. That sulfur is used one time and then disposed in a stack for perpetual storage as a hazardous waste. And phosphate production generally produces about 5 tons of phosphogypsum for each ton of phosphate produced. So NovaFos was looking originally at technology to make phosphoric acid without producing phosphogypsum. We use a carbothermal production method that produces high purity phosphoric acid, but also a calcium silicate product. And we have since evolved that technology to use it to recover sulfur for reuse and produce the same safe and valuable calcium silicates from phosphogypsum. In Florida, there are 25 phosphogypsum stacks. Where I'm at in my office right now, when I go on top of our acid plant, we're in the middle of the Bone Valley. I can see 7 stacks. We're in the middle of phosphate producing, so there's a lot of mines around here. And prior to 1991, a lot of the phosphogypsum went back in the mine cuts. And what's happened here is the permitting of new stacks is getting tougher. Lateral expansion is tougher. They're only getting taller, and they're some distance now from the chemical plant that produces phosphogypsum. And some of these are the slurry is transported 10 or 12 miles from the wet acid plant to a stack. In Florida, there's 1 billion tons of phosphogypsum currently stacked in Florida. About 30 million tons are added to this amount every year, and this equates to 50 tons per minute. So during this presentation today, a lot of phosphogypsum was added to these stacks. What is our process for processing phosphogypsum? It's a pretty simple process, again, that came out of our phosphoric acid production process. We mix phosphogypsum and sand into an agglomerate. We feed it into a grate kiln, a rotary hearth furnace, or a rotary kiln, and the off gas comes off for gas handling to recover the SO2. Most of the gas that comes off is SO2 to make sulfur products, including sulfuric acid, ammonium sulfate, and even clean gypsum, and then the calcium silicate product. And for about every ton of acid that we produce, we make about 1.5 tons of calcium silicate there. Um, how our process is different than other patented or currently proposed technologies. It really relates to how sand is used in the process. We don't use any carbon in the process. There's no catalyst, there's no hydrogen or oxygen added or aluminum additives in the process, and there's no melting. Our process requires specific times and temperature to achieve good sulfur decomposition and radon encapsulation. Um, the process can also be, it's not shown on here, as an interim step for fluorine recovery from the phosphogypsum. That can be handled as a separate product in the treatment process. And some of our consultants are using this technology or looking at this technology to treat other solid waste that contain similar levels of radioactivity and heavy metals. So this is the calcium silicate product that comes out of the process. We transform the phosphogypsum chemically and physically. We've tested the calcium silicate for toxicity and radiation per testing with the SRC environmental labs. The calcium silicate structure significantly reduces radon gas emanation from the phosphogypsum, which is the major exposure pathway for impacts to humans and the health. And the radon emanation that we see from the calcium silicate after we process it is equivalent to that of native Florida soil. If you look here, this is the some results that we've done for the radiation impacts of Novaphos calcium silicate. And the chart on the left there, you see the phosphate materials all contain radium. You see phosphate ore and Florida phosphogypsum. They all contain radium. The soil in the middle doesn't have much radium, but what we produced here, the calcium silicate, in the past we called these J rocks after our founder. And the calcium silicate we produce from phosphate rock or from phosphogypsum still contains radium. We don't destroy the radium or remove it. But if you look at the chart on the right there, we get the radon encapsulation from the calcium silicate. So you see the radon in ore and phosphogypsum, it's still rather high. There's some radon in Florida soil, but when you look at the radon coming out of our calcium silicate from the phosphate produced or derived calcium silicate or the phosphogypsum derived calcium silicate, you see that they're less than native soil, which, the soil in Florida does have some radium. So we've done risk analysis with the Oak Ridge Center for Risk Analysis, and they've concluded that using our calcium silicate in road paving projects result in negligible impacts on workers and the public. I'm really focusing today just on the use of the calcium silicate because that's really what has been our focus on this. When we were developing the calcium silicate from the phosphoric acid process, I met a guy here, Dr. Jamshi Armagani, who I call Dr. Concrete. What he doesn't know about concrete isn't worth knowing. And he's been, Mark, I really like your calcium silicate. What can you do to make calcium silicate other than using phosphoric acid? Because you guys are still developing that. So we moved on to phosphogypsum. And he's been really focused in leading our efforts to use the calcium silicate as an SCM or a supplementary cementitious material, displacing cement and concrete. Other SCMs, such as coal fly ash, are in short supply, and SCMs are having an increased value in the marketplace. And the testing that we have done, besides using this as a cement substitute, we can also use it as a lightweight or fine aggregate that is valued in concrete applications such as grid decks. It can be pre-wetted and has a very pozzolanic impact on the concrete products. We've also found that we can use it as a soil amendment to replace plant available silicon in some slags, blast furnace slags and steel slags. We contain more plant available in silicon than these other commercial products, but we don't have the heavy metals that are sometimes associated with steel slags. And just as an antidote here to what we're doing here, because I worked for a steel mill for 20 years, blast furnace wastes are a bevel waste that are excluded from RECRA. And there's really never been any issues with RECRA or NESHAPs with blast furnace slag. Just about every ton of blast furnace slag that was ever produced has been reused and consumed as a cement substitute or a fine aggregate. So that's just a little anecdote there. And with Dr. Armagani's help, we've been testing the calcium silicate in concrete as an SEM with the University of North Carolina. So when you look here on the charts on the left there, you see mortar set times. The gray is cement controls. The blue is the fly ash is an SCM. And the green is the calcium silicate, which we call J-ROX. And you can see for initial set times, we're a little bit better. And for the final set times, we're pretty close and being acceptable there. And then on the right, when you look at the mortar compressive strength in PSI, we lag a little bit with cement, but after 90 days, we exceed that. And Dr. Jamshed is very excited about using this as a cement substitute for fly ash and as a concrete aggregate, especially as fly ash availability in the US and certain parts of the world continues to drop. So this process provides better economics through sustainability. Each year, the phosphate industry generates about 30 million tons of gypsum containing about 6 million tons of sulfur with a value of $1.3 billion. Reprocessing this phosphogypsum could recover the sulfur to at least 90% so that it avoids having to purchase sulfur and then disposing of it as a waste in a stack. It reduces the need for stacks, the CapEx and OpEx and closure costs for stacks, and then using the calcium silicate as a SCM or a fine or lightweight aggregate also generates some revenue. And you can also get the revenue there from the recovered sulfur, which could be sulfuric acid, depending on your location, ammonium sulfate, or even clean gypsum, where the radon emanation is not anything near what phosphogypsum is. So we've been doing some lab testing on this process since the spring of 2022. And if you see on the left is our little lab furnace that we treat the phosphogypsum mix with sand at different times and temperatures. We do about 90 grams per test. Recently, we did some exhaust testing from that furnace for SOx and radon to satisfy EPA. And then we've also have a 5-meter rotary hearth furnace, which can process about 300 pounds per hour of feed to make the calcium silicate. And we've done that. And what we do at pilot scale replicates what's done at lab scale. We get 95% sulfur decomposition and greater than 99% reduction in radon emanation from the produced calcium silicate. And we don't see any radon coming out the lab furnace exhaust gas that could end up in the sulfur products, which EPA was concerned with. Oops. So right now, our current activities, we've submitted a petition to EPA about a year ago. They're still, with the government shutdown and everything and the turnover, we're still waiting for EPA comments regarding, they expressed some RCRA concerns based on this once being a RCRA waste, which is no longer RCRA waste, but they've expressed concerns based on the mixture rule and derived from rule. So we're waiting for those comments. The one thing that when we did first meet with EPA about a year and a half ago about the petition process, they did comment, hey, this is really novel what you guys are looking. Our rules for using phosphogypsum is taking phosphogypsum taking it through a black box, which is a risk analysis, and then putting it in the environment. We're taking phosphogypsum, mixing it with sand, running it through a black box, which is a furnace, and putting calcium silicate out in the ground and sulfur for recovery. And they said, this is a little bit different than what we're used to. And so they're struggling with that on how to handle our request. We've updated our radiation results by SRC labs and GEL labs to include gamma emanation. EPA was worried about that. And we've updated our risk assessment to really focus on radon, which is a indoor air pollutant, and what would happen in the plant as well as what happens out when it's in the environment. We have patents for this, or patents pending. We got a patent issued in August 2024 and a patent from the European office in September of 2025. We have a pending patent application with the US Patent Office and several other authorities. We expect those patents to be issued here in 2026. We're updating some engineering studies that Hatch Engineers has been doing for us for process design considerations, updating fact stage modeling, mass and energy balance, process flow diagram, block flow diagram, and the CapEx and OpEx. And we're looking at doing phase 4 calcium silicate testing with the University of North Carolina this year, with subject to the new ASTM standard, which is related to the use of supplementary cementitious materials. And we have evaluated several PG sources in our first facility location. We've done several site visits, and we've collected lab samples for testing and evaluation. And again, here's the patent that was issued by the European Patent Office in 2025 in September. It's got a duration of 20 years, and it covers 13 countries, including Morocco, which is a producer of phosphogypsum, which they're not looking for ocean disposal there and looking at recovering phosphogypsum. And then we have a U.S. Patent Office patent application that's pending. We responded to comments that the U.S. Patent Office gave us. They were very similar, almost identical to what we got from the European office, and we're expecting a similar result. So in summary, there, our process consumes and chemically transforms phosphogypsum. No phosphogypsum exits the process or is placed in the environment. We can produce 2 useful products that are safe: calcium silicate that can replace fly ash and displace cement and specialized aggregates. The sulfur gases, primarily SO2, can be used to make sulfuric acid fertilizers and avoid sulfur purchases. Other potential sulfur products include safe gypsum and ammonium sulfate. The impurities, primarily norm, as well, or from the phosphogypsum, are safely trapped in the thermally fused calcium silicate, even to a fine powder. All these tests grind this down to a 45 micron powder level. That's what you need to do in the lab to do the radon emanation. Our laboratory results for sulfur decomposition and radon encapsulation have been replicated at pilot scale. The risk assessments for processing phosphogypsum and using calcium silicate in concrete and road shows no impacts to workers in the environment. And again, we have some patents issued and others pending, and hopefully we get EPA approval here in 2026. And then finally, we did receive a Green Chemistry Challenge Award for this in September of 2025. The US EPA used to be associated with this program, but they're no longer. But the American Chemical Society continues to promote this program. And we received this Green Chemistry Award for a small business award category in September at the National Academy of Sciences. And we've been invited to present this technology at the Green Chemistry Challenge Award winners presentation in San Antonio in June, which we plan to do. 4 of the other awardees will also be presenting. So that's what I had there, and Any comments or questions?
Great. Thank you, Mark, for that presentation. There were a couple of questions came in here from Ed Weinberg. You can see in the Q&A. One is whether you're using natural gas to heat the furnaces that you use in Florida.
We use both. In our lab furnace, we use electric because that's kind of what you're stuck with. But in our rotary hearth and our kilns that we've tested, it's with natural gas.
Okay, great. And then the second question was whether you have, it says, if you have abandoned the PA plus JROCS approach, what is the reuse recovery of the P content of phosphogypsum?
Um, yeah, we're still focused on phosphoric acid production in another process with another technology that's covered by patents. There is some phosphate in the that's in the phosphogypsum. We're not looking at recovering that. Most of it stays in the calcium silicate. And for both products that we produce, the calcium silicate from phosphate ore and from phosphogypsum, the amount of phosphorus that's remaining seems to have no impact on concrete and cement properties and durability and characteristics.
Okay, great. I think that's it. We have no more questions in the chat. I want to thank our presenters for taking the time to prepare these presentations and deliver them here today. I want to thank all of you for coming to this webinar. As a reminder, and I'll put this up, share my screen here so you can see it. You can follow us on Blue Sky, YouTube, and LinkedIn. Our website is phosphorusalliance.org. And again, this presentation will be available on YouTube probably in the next week or so. Best way to do that is just to subscribe to our YouTube channel. And then when videos like this come out, you'll get a notification that they're there. We also have a newsletter you can subscribe to through our website at phosphorusalliance.org that comes out quarterly. I hope you'll do that just to keep abreast of what we're up to and what the phosphorus world is doing. Thanks again to our members for helping to support us, and I hope you all have a great day. And we'll see you next time for the Phosphorus Alliance webinar. Thanks. Bye.